Okay, so how's everybody doing? Good. Does it feel weird this week not having an assignment hanging over your head? Somehow it's a bit of a letdown somehow. So this week is basically devoted to review. You may or may not have noticed, but classes started on a Thursday this semester. And since we have class on a Thursday, that means we have one more class than some other courses. So one more lecture than some of those other courses. Which means that, I have a bit of extra time. So I would like to spend this class doing some review, basically talking about, reminding you what the course was about, where you started maybe, and where you are now. And then next class, if we don't finish that today, we'll continue it next class. But next class will be sort of an open thing. I'll bring some example questions to work on, so things that you might see on an exam, but you can also ask me anything at that point. But before we do that, I want to have the talk with you. So it's time for the talk. For most of you in this room, it's probably not so relevant, but for some of the people listening to this video, it may be relevant. And this is a talk about me. So I was a student once, and I came to university fresh out of high school. And I thought I wanted to be a chemist. So I took chemistry courses. And what I quickly learned is that chemistry was not for me. There seemed to be, at least in the first parts of a chemistry degree, a lot of memory work, a lot of slow, painful, tedious lab work whose outcomes could normally be predicted before doing them. I understand that chemistry gets more interesting as things go along, but what I discovered while taking these chemistry courses and taking other courses like geology, I never took a physics course. Maybe I should have been a physicist. And taking an introductory programming course, what I discovered is that my intro programming courses were a lot more interesting than anything else that I was taking. So by the end of my first year, in fact, I'd already more or less decided this by Christmas of my first year, that I was going to switch into computer science. So all of that to say, if you're taking this course now, so you're taking this course, it probably means that you're looking to do a computer science degree. You've somehow signed up for some kind of computer science degree. And if you're taking this and thinking, wow, this is awful, I really hate what I'm doing, but I hear that there's good jobs in computer science, so maybe I'll just stick with it for the next 3.5 years, and then for the next 40 years of my life, I'll keep doing this thing that I hate. Don't do that. So now there's nothing wrong with, you're not quitting if you change programs and decide to do something more interesting. You're doing the right thing. So if you find that this is not for you, don't think of it as, oh, computer science, I'm going to quit it, or I don't feel bad about that. This is a positive decision. I mean, change into something that you do like doing. Do something you love. Don't just stick with it because you think you should. Like I said, that probably doesn't apply to a lot of the people in this room. The fact that you're sitting in here right now already says something about you. But maybe some of the people listening on this video. So don't be afraid to change directions. It's still really, really early for most of you in your academic career, and you really will have lost nothing. I mean, you switch into another, doesn't matter what university program you switch into, just about everything you've taken this semester will count as an elective in some other program. So it's not a problem. Okay. Any questions about that? No? Good. So feel free to ask me for, career or course advice after the fact if you want. So what I'd like to do then, the way I'd like to structure this review, is talk about what the intention was for you guys to learn in this course, the so-called learning objectives, and then see how we manage to fulfill those objectives or maybe not fulfill them. You can decide for yourselves. But the main sort of learning objective for us, the main goal in this course was for you guys to become proficient in some programming language. So if you came into this program, into computer science, already being an ace programmer in some language, you could actually test out of this course and skip it entirely. So the goal by the end of this is that you're a good programmer in some language. Presumably, by now that language is Python. Okay, so that's sort of goal number one. That's really just so that you have a way of expressing yourself and expressing some higher level concepts. One of the more high level things that I wanted us to learn about is learning how to solve computational problems. So it's not really until you see a language that you really understand and work with a language that you really understand how dumb computers are. They're very fast at doing very simple, specific, precise things, but they know how to do almost nothing complicated on their own. If you want them to do something complicated, you have to write, give them specific instructions on how to do that. And that, that involves learning how to solve problems computationally. Another objective, and this is something that was just intended to give you a flavor of the kind of thing that you will end up doing if you take a career in programming, is learn how to do I won't say large scale, let's say medium scale project using third-party libraries. Okay, so something beyond just writing short little functions that do simple, isolated little tasks. Something that has a lot of parts to it, interfaces, and just a bigger project than the sort of exercises that we do on the typical assignments. One thing that we needed to learn is how to do event-driven programming. So that's a style of programming where you don't just write code that starts executing and executes from beginning to end, but rather code that sort of runs and sort of hangs around waiting for things to happen and then responding to these things that happen. You have written code like this. And this is important because anytime you want to do anything that has an interface, so anything with a user interface, you end up doing event-driven programming. It's not cool for programs that are waiting for user input to sit there in tight loops, consuming 100% of the computer's CPU time, just listening for someone to do something. They have to instead wait. Same thing is true if you want to do anything that does any kind of network programming. Most network programming involves waiting for a network connection to become available, sending something across that connection, and then waiting for a computer eternity for some data to come back across that connection. Again, that should all be event-driven, where the program is usually not running, it's just waiting for something to happen. Learn about recursion and how to use it. And learn about efficiency. And by efficiency, I mean computational efficiency. So I'll get into all of these things in more detail and when we talk about the topics that touched on these things. But these are all things that you may or may not have known about before you started this course, but now you have a better grasp of them. And finally, this is not a course objective that I particularly cared about, but it's one that you sort of need to get through, is to learn about rudimentary Java programming. The reason for this is more of a practical one. Next semester, many of you will be taking Comp 1406, which is Java/C++ programming. And those two languages are so far away from Python that I don't want to just throw you in there completely empty-handed, although they sort of assume you don't know anything in there. I think these last couple of weeks will help you with that. So that's more of a practical issue more than something that it was really core to the course. Luckily for us, Python is such an easy language to learn that we had those 2 weeks to do that. With a more complicated language, we would have been struggling right to the end to even get up to maybe the 5 of these learning objectives. In Python, things can go quickly. We don't get too hung up on the language. Okay. So, any questions about these things? What these mean, what they were intended to be? Yeah? Processing is not really a language. Processing is a library on top of Java. So that makes it more complicated because you can write arbitrary Java code in processing. And so it's the more complicated language, whatever that means. I guess I could ask you guys, do you feel that you missed something by not learning processing?
Absolutely not.
Okay. So, yeah, okay. So the sort of main advantage of processing, at least as I see it, is that you immediately are doing graphical things. And for some people, that helps. That's much more intuitive and helps them get through things, understand things more quickly. That sort of happens immediately. But processing is, of course, something on top of Java, and so really you're still programming in Java. You're still bound by types and all this stuff. And very quickly, as you try and do more complicated things, all that kind of catches up with you, and it becomes more work to do the similar things. The advantage of Python, of course, is that it's cleaner, and I think because of that, we actually get to a stage, assignment 8 being that stage, where you do something fairly big and substantial that's also graphical, but is a little bit more meaty than maybe you would get to if you had to do all of that in Java, for some of you. So I won't say one is any better than the other. Although, when it comes time to apply for jobs, for those of you going into co-op, which will be the end of next year, you'll have 2 programming languages on your CV, Python and Java. Processing is not, like I said, it's a library on top of Java, basically. Okay. Other questions? So that was one person who was outspoken, said they didn't feel they missed anything. But is there anybody who feels that they would have been better served by the other section? No. Okay. They're probably in the other section. Okay. So become proficient in some programming language. Well, what do you need to do to become proficient in a programming language? Well, you have to learn about the basic constructs of that language. Luckily, these things are fairly portable, and most languages have some version of all these basic constructs. We have variables. Basically, from day one, we defined, variables x and y. We set them to values, and we use them. Most programming languages have some notion of a function, at least all of the less exotic languages. And again, on day one, we were defining functions, areas of circles, triangles, whatever, you name it. You're only 3 letters away from defining a function, DEF. Even in a language like Python, which is not typed, where variables don't have a strict type, you still need to know about the data types. So once you assign something to a variable, whatever you assign to it does have a type. And we saw, the basic ones, numbers, and different kinds of numbers, integer, floating point. We saw that there's pitfalls already. As soon as you start using floating point numbers, you get strange results like 0.3 minus 0.1 is not equal to 0.2. It's just a little bit off from that. And, another basic type is strings. So those are sort of the basic things. Just about every language has some form of array. Yep.
For the exam, should we brush up on like operations with floating points? Like, will you ask us what this floating evaluation evaluates to or expression?
No, I don't expect you to know that 0.3 minus 0.1 it gives you a number which, when you display it in all its glory, is 0.19999999999. That would be a lot to ask. But you need to know that these kinds of things can happen. So, for example, here's something really dangerous to do. Let's say I equals 1.0, while I is not equal to 10. I plus equals 1. So this is something you only need to know about floating point imprecision to understand that this is a dangerous thing to do. So why is this dangerous? Yep. It may never actually equal exactly 10, because it starts out at 1.0, which is like really close to 1, but not exactly, maybe. We don't know, because there's always this imprecision. And then we keep adding 1, so it'll go to something close to 2, and then something close to 3, and something close to 4. By the time it gets up to 10, it might actually be 0.999999999, and then jump from there to 10.9999999, never being equal to 10, in which case you get an infinite loop here. And it's kind of hard to predict. Yeah?
Is there some way to know what it will equal, or is it just...
No, if you really need to do something like this, you really want something like while I is less than 10. And do something robust like that.
Or is there ever a way to know like what a floating point value an expression will evaluate to?
Well, I mean, what do you mean what it will evaluate to?
Like that 1 point or 3.0 divided or minus 1.0 will equal 1.99999.
Yes, the floating point representation, it's an IEEE standard, so it's completely well defined. The operations are well defined and everything, and nowadays modern processors implement this specification exactly. So if you really wanted to know, you can see what the binary representation of 0.1 is, what the binary representation of 0.3 is, what happens when you follow the specification and do the subtraction and see what the resulting floating point binary representation is. That's a super painful way to do that kind of thing. What happens more, what you're more likely to do is say something like, I will use floating point numbers, and when I present them to a user, I will only show, for example, 2 digits of after the decimal place. And so if you can do that with string formatting, the percentage 0.2f or something. And if you do that, and you know that your numbers never get really, really big, then you can assure yourself that everything you show the user looks like it's completely 100% accurate. Even though there is some error in the lower digits, when you convert and only show the 2 most significant digits, it'll do the rounding up or rounding down that actually makes it accurate.
Did you say we do that by doing the percent sign and then like 0.2f or something?
Yeah, so what did I say? It was 0.3 minus 0.1, right? So that gives you this, this thing here. So if I say x equals that, well, x is still equal to that, but if I say, let's format that using 2 decimal places as a floating point number, then you get what you expect. Okay. So even though behind the scenes there's this small inaccuracy in what you present to the user, that never shows up. And that'll work as long as your numbers never get really, really big. So if your number here got into the hundreds of billions, then actually you may even make mistakes in these lower digits. For that, you need to sort of understand how the floating point representation works. Yeah?
If you wanted a more accurate representation, can you use fractions class?
Yeah, so Python, if you really care about these things, has a fraction class. We didn't talk about it. So I think I need to import a fraction. Or is it fraction? Fractions. Okay. So there is this thing called fractions, a module called fractions. It has a class called fraction. And you can do things like, say, fraction, well, 1/10. So that's A, B equals fraction 3/10. It's B, and if I say B minus A, I get a fraction of 1/5 or 2/10, what you expect. This will do exact arithmetic on fractions, but just don't use this anywhere, just everywhere, because this, because it's doing exact arithmetic, it may have to make, denominators that are huge to get the number exactly. So your program could get significantly slower depending on what kind of arithmetic you do. And fractions can do, I think they'll do these nice conversions for you. So if I convert that to a float, it'll give me the 0.2 that I expect. Okay. Other questions? Yeah?
You can use fractions with any operation? Like variables fractions?
Yeah, so let's try 5 plus a is a fraction 51/10. So once you mix a fraction in there, it becomes part of this thing. But what happens when you do a floating point and a fraction, then you're using this floating point. It's already imprecise. It's just going to do everything in floating point. Same way when you mix integers and floating points, it throws away all the exact arithmetic. Yeah?
Could you read one more time when it's a bad time to use fraction?
When it's a bad time to use fraction? Well, it can be bad if you're doing calculations where they keep building on each other. Like, you have a counter that's adding up a bunch of these fractions. So, if you want to do exact arithmetic on fractions, what you need to find, you add one fraction A and fraction B, you need to find the least common multiple of their denominators, and that can be big. And now you come along and you take another one and try and add it in there. That may again have a bigger least common multiple in the denominators. So eventually, In fact, I did some simulations with this recently for something that I needed to solve exactly, and I was getting fractions in which the numerator and the denominator had like 100 digits, basically. So not, that gets expensive to do these kinds of operations. And that wasn't even a particularly big simulation. Okay. All right. So so next up was arrays. Python doesn't actually have arrays or raw arrays that you can access, but close enough is Python's lists. Python's lists are just arrays that will grow or shrink as necessary. Not every language has those, or at least not as a primitive data type. Looping. So we saw for loops, which loop over the elements of arrays. And up until that point, we were actually, right to the point of for loops, if we didn't use recursion, we're actually not able to write every program. So in particular, if you only use for loops, Python's for loops, which iterate over arrays, and you avoid recursion, then it's impossible to write a program that doesn't terminate. So it's impossible to write an infinite loop using just these constructs. You can write programs that run for a really, really, really long time, but you can't write infinite programs. And actually, if you ever learn a little bit of the theory of programming, it's not even programming languages, but the theory of what's called recursive functions, up until this point, you've learned about primitive recursive functions. As soon as you hit while loops, all bets are off. So up until this point, there's a lot of really interesting things and theory about programs. In fact, there are programs that can analyze programs written using only those constructs and tell you stuff about them, tell you how long they'll run for, when they'll terminate, they all terminate, so that's easy. Reason about them. But as soon as you have while loops with arbitrary stopping conditions, all bets are off. You can do anything. It's very easy to write an infinite loop. Very difficult. In fact, it is impossible. It's what's called incomputable to know whether one of these programs stops or not. So there we get to the full kinds of bad, the worst things that can happen, as well as the most powerful things that can happen. And branching. So those were if, elif, else, and user input. And the user input we saw was pretty simple, print and raw input. So that's sort of basic programming stuff that happens at the terminal. But you can write anything in this. I mean, you can compute anything that can be computed, you can use just using these constructs. So basically, in the first 3 weeks of this course, we learned about everything that computer science can do. There's nothing that can't be done with a computer that can't be done using just these constructs. Then we saw some more advanced concepts, some of which are in Python and not in other languages, but most modern languages have these things. Advanced concepts. Exception handling. So what to do when things go wrong, like the user is supposed to enter a number but they entered a string, causes something to crash or throw an exception. And we saw that there's this try except mechanism that you can wrap around these problematic bits of code. If something goes haywire inside that code, you can gracefully get out of there and ask the user to try again, or quit and print a helpful error message, however you think you should handle it, but not handle it by having the program just print some garbage, say that there was an exception and stop running. And exception handling is a huge part of a lot of programming. In particular, any kind of programming that involves interaction with anything outside the CPU and memory, basically. If you need to access things on disks, sometimes disks fail. If you want to recover from that gracefully, you need to handle those kinds of exceptions. If you interact with users do dumb things all the time. You ask them for numbers, they give you strings. You ask them for strings, they give you numbers. You ask them to click the mouse and they close the computer instead. Lots of exceptions when you're dealing with users. Same thing if you're doing any kind of network programming. And their exceptions can be just, networks are not reliable. Half the time the wireless network doesn't work in this room. As well as being not reliable, there are sometimes people, agents on these networks that want to do bad things to you. They're deliberately trying to break your program, make it do something it's not supposed to do, and you have to watch out for all that. And exception handling, this kind of structured exception handling, helps a lot with that. We learned about objects. So these are just, you can think of them as new data types that you make from existing data types. So, you want to have a point type which has two coordinates, x and y. Well, then you can make a point class. Two of the instance variables of that class are these coordinates x and y. And along with that comes the ability to make special functions that operate on points then. So-called instance methods. So in Python, these are called properties and methods. Properties are the data that's associated with an object, and methods are the functions that are associated with an object, so the functions you can use on them. As part of that, we learned about inheritance, how you can have one class of object which is a special case of another class of object, and it inherits all its methods. I think we did examples like a musician is a special kind of person. We had examples in our game of special kinds of missiles. There was a missile class and then certain special kinds of missiles that split or are incoming missiles. So we have that. And this word that we avoid using because I don't like it so much, polymorphism. That's just objects that, a way of using objects where you don't exactly have to know what kind of object you're dealing with. You just need to know that it supports the operations you want it to do. And for that we do all the time, right? We write functions that take two numbers and do something with them. Maybe they add them together, maybe they multiply them, maybe they compute the area of a triangle with those things. And those functions, they'll work whether the numbers we give them are integers, whether the numbers we give them are floating point. In fact, even if the numbers we give them are fractions, they'll continue to work. So we don't really care exactly what kind of numbers there are as long as they support the operations we need them to. Addition, multiplication, whatever the function needs them to support. You could take whole courses on object-oriented modeling. That is, deciding which classes you should make for your application. We luckily did a lot of simulation and gaming stuff where the classes are fairly obvious. They're really right there on the screen. There's a missile, there's a base, there's whatever. So games are nice for that. A lot of the classes jump out at you. The modeling is easy. Okay. So that's basic, one programming language. And there's very little in here. In fact, there's nothing in here that's not available across a wide variety of languages. So in C++, in Java, all of these things exist. Exceptions, objects, properties, variables, functions, data types, all of that stuff exists in pretty much every mainstream programming language. In some of the older languages like C, objects are a little bit less restricted. C has things called structures where you can create compound data types that have properties and values, but they don't really have functions that operate on them. They're a little bit sort of a weak form of objects, and there's not really inheritance there. You have to kind of fake it if that's what you want to do. Now, that's not the main subject of the course, though you may or may not be surprised to learn. This was not the point, learning all this stuff. This is just somehow the tools that you need to express other things. So, for example, if I wanted to teach you a course that was about music and making music, well, ultimately what I want to teach you is how to compose things, some of the music theory, but to really know if you're making music properly, it's nice if you're able to play an instrument. So, you compose your music and then play it somehow. And this programming language learning a programming language is really just about learning to express your ideas for other things. And really the main subject of this course is how to solve computational problems like this. So you're presented with a data processing task, and if you think about it, many things are data processing tasks. So you may say, oh, I don't want to do data processing tasks, I want to make apps. Or I don't want to do data processing tasks, I want to make games or something. But every little piece of an app or a game usually involves some data processing task, right? I mean, even the act of advancing a game from one frame to the next, which happens 30 times per second, usually involves a bunch of data processing. We have to go through a list of all the game objects and see that they're updated in very specific ways that matter for them. We may have to do fancy things like check to see if there's interactions between game objects. There's lots of data processing that needs to be done there, and this happens 30 times a second. So we need to know how to cope with these kinds of problems. And the kinds of computational problems that we learned to cope with, they sort of mirrored the way we learned the language. So, or at least the basic constructs in the language. So the first thing we learned how to do was write straight line programs. So what are straight line programs? They're programs with no branching, no loops, no arrays, nothing. They're just sequential lines of code that just execute one after the other until the result that you're looking for is computed. You did that on the first assignment. So anything that's a conversion, anything that the BMI calculator is one of those, for example. Just applying some formula that may be complicated, and it may not just use numbers, it may use strings and other things, but there's no decisions to be made in your program. It's just straight things to execute. And the nice thing about straight line programs is these always run in constant time. In fact, they only take time which is as long as the length of the program, the number of instructions in your program. So if you can solve a problem with a straight line program, that's great. It's going to be a really fast solution. So what comes next? After you learned about straight line programs, what other kinds of problems did you learn to solve? What was the second assignment about? Yep. control structures. And there, the first one, because it's not too wild, was iteration over an array. So a lot of things, in fact, a ton of data, huge amounts of data processing is just iteration over arrays. You know, all of the most basic ways of searching things is this kind of iteration over an array. And it seems to happen sort of all the time. When you, I mean, even something as simple as your phone, when you start, let's say, dialing a number on your phone or entering an email address, what immediately comes up is a bunch of completions of that thing. And you're thinking, well, how does it come up with this? Well, you've got an address book on your phone. The most likely thing that's happening is, as you type, it just goes through that whole list of, of items in the address book and selects the ones that match what you've typed so far. That's just an iteration over array. We know in Python that you could do that using a list comprehension with an if clause in it. So I mean, you could easily express that that kind of thing. It's one of the most common sort of solution types that is not that's not constant time, that requires some iteration. And it's also not out of control. It's really a finite thing. It iterates over the array, and that's it. So these things, provided you don't do anything fancy in there, these run in linear time. So linear in the length of the array. These run in constant time. So let's reorganize this a bit. So problems that you can solve that way. Good. What sort of came next in our problem-solving toolbox? So we did iteration over arrays and a few other little iterative things. Then already we wrote a game. So the third assignment was to write a game. Then what did we do after that? What kind of tools did we pick up? Sets and dictionaries. So we saw that a lot of problems, which look kind of difficult on the face of it, you can solve really efficiently using sets and dictionaries, using the fact that sets and dictionaries can store arbitrarily huge amounts of data, but you can still access any data in there in constant time. So those were things like removing duplicates from a list. Those were things like, you know, we did several versions of this, find items that also appear negated. And lots of variants of that. There were things like anonyms. We even saw that you could do anagrams this way. And we did frequency counting. So counting how often words occur in a text. All of those things we could do very efficiently using sets and dictionaries. And basically the strategy there was, it's one loop that iterates over an array of all the words, or an array that we're trying to remove the duplicates from. And inside that loop, we use a data structure, a set or a dictionary, to accomplish what we're trying to do. So we're using a set or a dictionary, but that's in conjunction with iteration over some array. Any other little tricks that we learned? So we saw straight line programs running constant time, things that we can solve by iterating over an array, even if we have to use a set or a dictionary to help us. They can run in linear time. Was there anything in between those two? Yep. Yeah. So there, what we really learned about are problems solvable using binary search. And they all have kind of the same flavor. They're all the flavor of this guessing game where the thing that you're looking for is somewhere in an array, and you have some way of, if I just pick a random location in that array, knowing whether I picked something that's too big or too small, whether I'm too far into the array or not far enough into the array. And that allows you to do this, this repeatedly halving the size of the array. So the basic thing is finding things in a sorted array. The 1,000 number guessing game. Binary search is actually a useful thing, even outside of a program. It's something that we tend to do, or we should do frequently, even when we're doing things ourselves. So those usually lead to O log n running times. So running times that are, for 1 million elements, you're talking about 20 different comparisons. Okay. Then we got to some harder problems. Problems requiring, let's say, nested loops. So for example, I give you an array and I ask you something like, let's what's a good example? Well, okay, so it's hard to say when a problem requires a nested loop, but there's lots of problems you can state as something like, tell me if this array contains two values, a at I and a at j, such that they have this property, some property. Maybe it's that their sum is equal to something, or maybe it's that their difference is equal to something. Those are not great examples. But sort of two nested loops. So, find array indices ij having some special property. And sort of the obvious way to solve that is to try all values of I and all values of j. And sometimes you want to allow things like I and j to be equal, and sometimes you don't, and there's slightly different ways of writing the loops there. But if you find yourself reduced to doing this, you know that you're making slow algorithms. So there you're ending up with algorithms like running times of n squared. And in between all of those things, there's another class of problems, and those are problems that are easy after sorting the input. So for example, I think this may have been an assignment question. I give you a list of elements, and I say, find two elements, two distinct elements, whose difference is minimal. Okay? So, you know, you have a list of numbers, and I want you to find AI and AJ so that if I take the difference, AI minus AJ, let's say the absolute value of that is the smallest possible. So that immediately is one of these problems you can solve by trying all values I and j. But if you think about it a little bit, you realize that if you sort the values, then it becomes really easy, because the two closest values are going to appear side by side in sorted order. So if you sort the values first, then you just scan the array looking at each value and the next one in the array. The answer is going to be one of those things. And that means there's only n minus 1 things to look at instead of n squared things to look at. So these are things like finding the two closest values in an array. Which, if you think about it, is really a special case of, or a generalization of, things like removing duplicates. So if there's two values that are equal, they would be duplicates. You could find them using a set or a dictionary. But if they're not equal, sets or dictionaries don't help. But sorting does help. So you can solve it easily after sorting. Okay. And those are the main techniques we've learned about in this course. A huge part of computer science is the study of algorithms, which is what this is really talking about. And this is far from an exhaustive list of algorithmic techniques. These are just the first things you try if you have a computational problem you need to solve. Interestingly, the more and more you do algorithms, the more and more you realize that it happens a lot that either one of these things works, hopefully something before the last one, which leads to slow algorithms, or actually nothing works. There is no real efficient way to solve your problem, and you have to somehow change the problem. So a lot of things you'll learn are simply not efficient to solve using computers, at least not exactly. So you have to make some trade-offs. Medium scale project using a third-party library. What was this? What was the library and what was the project? Yeah. Yeah. So the third-party library was Pygame. You had to learn how to navigate this awful documentation that is the Pygame documentation and figure things out from there. I introduced you to a few things, but there's a lot more in there, and some of you discovered a lot more of those things yourselves. So that's it. And assignment 8 was the project. And what you'll find, anytime you make a project like this, or anytime you do a project or get involved in a project, this is really a lot of what you end up doing is looking at documentation, learning what the capabilities are of the libraries that you have available, deciding how to use them. Sometimes not everything is not perfect. Like in Pygame, some sound files work, some don't. There's sort of different things you have to work around. These are all things that come up on real projects. Notice that these were not issues that came up with these other little sort of toy assignments where it's, write a function to do this, write a function to do that. But as soon as you want to do something real, then you start running into things that are not so pretty. And in many cases, that's the most interesting part of doing stuff is finding workarounds for that. Event-driven programming. That was Pygame. If you remember, the structure of the games that we made are the game initializes itself, and then it enters a loop, and at the top of that loop is pygame.event.wait. So that pygame.event.wait is not a function that returns immediately. It's a function that hands off to the operating system and says, tell me when something interesting happens. And if you want something interesting to happen periodically, you can set timers which generate these timer events, or you can wait for mouse buttons to be clicked or mice to be moved, or any number of things you want to do. So Pygame and the Pygame event loop. So after that, we got into recursion, and there, there's this whole question of first expressing a solution to a problem recursively, and I think I don't know, was it last class? For some of you, it's still a little bit magic. So, you know, things like factorial, you understand, and even things like a recursive binary search seem clear. But when we did merge sort, I think that was sort of magic to some of you. The fact that you can recursively sort the first half and recursively sort the second half, and then those are sorted. That's something that you'll need to spend some time wrapping your head around. So, you know, the basic strategy for recursive solutions is twofold. First thing is, you know, you need to define base cases. These are things that are easy to solve, that are small enough to just solve immediately. And then you need to express the solution as a combination of solutions to one or more smaller subproblems. So sometimes that's really easy, like the factorial function. What's factorial of n? Well, it's just easy from the formula to see that that's n times n minus 1 factorial. So n minus 1 factorial is the smaller subproblem, and if I want n factorial, all I have to do is take that thing and multiply it by n. For an algorithm like merge sort, there's substantially more going on. If I want to sort a whole array, yes, I can sort the first half recursively. Yes, I can sort the second half recursively. But then there's still quite a bit of work to do to take those two sorted halves and make them into one fully sorted array. There's this sort of intricate merge function that you have to write. It's not always obvious how to do these things. So, you know, there's this implementing recursive functions without, you know, doing infinite recursion is already a challenge. But beyond that, you know, if you want to do this reliably, you need to understand and analyze recursion depth. So we saw right away examples of things, algorithms on things like lists that blow up if you give them a list with more than 1,000 elements. And to really understand why that's happening, you need to really be able to look at a recursive function and understand how it's going to execute, drawing one of these recursion trees and seeing, you know, how big is the stack going to get for this function. And it's tricky. You really have to understand these things. Sometimes, you know, even for people with PhDs in studying this stuff, it's not obvious what the recursion depth is for things. Luckily, there's a few common patterns. The two basic ones are you recurse on a little nibble. So you have an array of size n. To solve the problem, you recurse on an array of size n minus 1 and then do something. Then the recursion depth becomes n. That's usually bad. It means you'll crash when n is bigger than 1,000 in Python. The other pattern is what we saw with merge sort. It's the typical so-called divide and conquer pattern, where you have an array of size n and you chop it into two parts, each of size n over 2. And there the recursion depth is much less. It only ends up being log n. So we've drawn a few of those recursion trees. And binary search is another example like that, where to search in an array of length n, I actually chop it up into 2 parts, and I recurse on one of those parts. So again, there the recursion depth becomes log n. So in general terms, log n recursion depth is probably okay. A recursion depth of n is probably not okay, at least for large values of n. Yeah. So just to write down what I said, if I reduce to a problem of size n minus 1, leads to recursion depth of roughly n, reducing to one or more problems of size n over 2 gives a depth of log n. So avoid these solutions that just take a little nibble, take one piece out of the input, and then recurse on the rest. They usually lead to high recursion depth and are often inefficient. All right. And next, we wanted to learn about computational efficiency, and that is really the analysis of running times. So, you know, someone gives you a piece of code or describes how a piece of code works to you, you should be able to give rough estimates on how long it's going to take if you run it on a list of size n, so a list of size 10,000, a list of size 1,000,000 or whatever. That's what running time analysis is about. And there's a few tools associated with that. We saw this big O notation. We never formally defined it, but you can think of it as just drop all the leading constants. So for example, if you see a for loop that executes n times, and inside that for loop is just a few simple instructions, then you say that runs in O of n time. Doesn't matter really whether those instructions are additions or multiplications, or whether there's 10 of them or 3 of them. That's not going to be the big difference. The real important thing is that they run, each of them executes n times. So that's the sort of big O notation that we've been throwing around. If you're taking 1805 now, any of you taking that? Yeah, so you've learned really what big O notation means. It's about sets of functions, but we still toss it around in this way. We've seen the common running times, which really mirrors our common techniques for developing algorithms. Straight line programs give you constant running times. Binary search gives you log n running times. Iterating over arrays gives you linear running times, sometimes in conjunction with using a set. And then you get into the bigger ones, things like n squared if you try and iterate over all pairs of elements in an array. And sorting squeaks in there right in between with a running time of n log n. That we analyzed fairly carefully last class when we studied merge sort. And these are, from left to right is preferable, right? These are the smaller running times on the left going up to slower and slower running times on the right. Okay. One thing you should sort of get familiar with is don't think of these as really abstract things. So we saw, examples of these things, not just as this funny O notation that looks impressive or something, but these really have to do with actual time it takes to do things. So it's good to be comfortable with these running times and what they look like for typical numbers. So for example, O of 1 really means just a constant, a few lines of code. Something that actually probably executes on your computer in like a millionth of a second. If it's really just a few instructions, you're talking like, a millionth of a second. So a teeny tiny thing. O of log n, remember what that thing looks like. So let's make a little table. We have O of 1, O of log n. So if n is like 1,000, well, O of 1 is still exactly that, O of 1. What's log n if n is 1,000? It's about 10. 10. And if n is 1,000,000, what's log n look like? Yep.
100?
Nope. Nope. 20. So it's only about 20. So n increases by a factor of 1,000. The running time increases by a factor of 2. And if n is 1,000,000,000, what does log n look like? It's about 30. So every time n increases by a factor of 1,000, log n increases by 10. Not a factor of 10, but just 10. So really, if you have something that runs in log n time, it's almost, it's not quite, but it's almost doesn't matter how big the input is. You can now go up to 1,000 billion. So that's like terabyte is the word when you express that as the size of the data. Then log n is 40. So nothing huge. Yeah.
Is that log base 2 or which base?
That's log base 2. But again, in big O notation, it doesn't matter whether it's log base 2 or log base 10 or log base 3. All that would change is instead of these numbers being 10, 20, or 30, they might be 7.5, 15.2, and 25.2 or something. Nothing. It only changes them by a small constant. It doesn't affect the fact. The difference is still enormous between 1 billion and 30 or 22 or whatever the number is for a different base. Whereas, O of n is just that. If you have an O of n time algorithm, you run it on something of size 1,000, it'll have to do about 1,000 instructions. You run it on something of size 1,000,000, it'll have to do about 1 million instructions, and you run it on something of size 1 billion, and it'll have to do about 1 billion instructions. Still pretty fast. Like 1 billion is not a huge number for a computer. That's the kind of thing that maybe not in Python, but written in C or C++ would run in a second or two on a machine like this. Where things really fall apart is, well, we can do n log n. N log n, we know what that is now because it's just the product of these two things, right? N log n, if n is 1,000, is log n times n, so 10,000. If n is 1 million, it's 20 million. And if n is 1 billion, it's about 30 billion. So not much bigger. I mean, in fact, bigger by factors of 10, 20, or 30. But things really get out of hand beyond that. So n squared, for n is 1,000, you're already talking about 1 million. So already that's something that written in Python would take, you know, half a second or something. If n is 1 million, then you're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You're looking at 1,000 billion. So, you know, the equivalent of a terabyte worth of instructions. Right, so I said that, you know, in a language like C++, 1 billion instructions might be something that happens in a few seconds. Well, now this 1 million items takes a few thousand seconds to process. So you're looking at, well, 1,000 seconds might be 15 minutes or something. 20 minutes. And, you know, if you have 1 billion, you're out of luck. It's never going to finish. So that's, you know, the number of instructions it's going to take you on an input of size 1 billion. And doesn't matter what programming language you use, that's not going to help. Because there you're waiting for, you know, at least 1 million seconds. So whatever that is. Okay. One thing I would like you to keep in mind is a good number is n being roughly 10,000. Know what all these things mean for n equals 10,000. It's the kind of thing that shows up on exams. It's about 13. This is 10,000. This is about 130,000. And this is 100 million. And something else we looked at was the efficiency of two sorting algorithms. So we looked at bubble sort, or not bubble sort, but insertion sort. And we saw that if you give insertion sort an array that's sorted in reverse order, then it basically takes each element of the array and slowly moves it up to the front of the array, one element at a time. And that leads to a running time of n squared. And we looked at merge sort, which, after carefully analyzing the recursion tree, we saw gives a running time of n log n. Okay. And, you know, we briefly tried to understand the running times of recursive algorithms. Merge sort was an example. Binary search was another example. There's no general way to do this for every recursive algorithm, but the best strategy is to start drawing one of these recursion trees, trace the execution of this thing, and see how big it gets. And then finally we finished off, just out of necessity, with some rudimentary Java programming. The main differences between Java and Python, you have typed variables in Java. So everything has a type, and it's not just variables, but function, return types, and function arguments. They all have very specific types that you have to specify. Java's native types, things like char, short, int, float, double, long, string. We learned about these modifiers: public, private, protected. These are things that parts of objects you can say they're free for anybody to use, not free for anybody to use except this object itself, or protected, which is somewhere in between. And there's even a type called friendly. If you don't specify anything, then you're sort of half protected. Things in the same package can use it. And every part of every object has one of these things. It's either public, private, protected, or friendly. We learned about static versus non-static. And in Python, those are basically functions versus functions inside a class. We learned that Java has real arrays, not like Python's lists. And Java also has some basic data structures like Python does, but they're a little bit more work to use. There was list and array list. There was set and hash set. And there was map and hash map. And these correspond to Python's list, Python's set, and Python's dict classes. And I don't know that we talked about this, or we did an example of this, but there's also exception handling in Java. It works almost exactly the same way, except instead of try and except, it's called try and catch. Okay, so that's a good place to leave it for today. Next class we'll go over the exam format in detail.
I ask a few questions about my degree.
Mm-hmm.
Like, so